everyone. Now we continue with the Emre, Anıl, Oğuz. So his mentor is not available right now. He's a student at teacher. He's a mathematics engineering student. His title is the most interesting one. So it is transformers are all you need. Now the stage is yours, Emre. Thank you.
Hello everyone, I'm Emre Anıl. Today I will be presenting you the fundamentals of large language models, which are transformers. We have studied the core components of the transformer architecture with Ozan Evkaya, who is my mentor. We try to gain a deep understanding of about their working mechanism. So let's see the first table of the table of contents. In the beginning, I will be talking about the how we identify these large language models, how we use them, how they specialize on different tasks. And after that, I will be talking about transformers, which is our main topic today. And after that, I will show you some comparison between two text generation models. And at the end, if you have any questions, I will answer those. So as an introduction, by large language model, we mean deep learning models that specialize on text data. So we have some text input and we are giving it to a model as an input. And then we are expecting to generate the text or summarize the text or translate the text. And actually, most popular one is the ChatGPT, which one of the question answering large language models. In 2017, a paper named "Attention is All You Need" is published. So at the beginning, it didn't draw too much attention, but after 1 or 2 years, it became the main architecture for today's large language models. And paper introduced us to how we should approach the data, what can we extract from it, and maybe the most importantly, how we can reduce the training cost of a large language model. So I will be talking about the encoder part of the transformer. Encoder and decoder are nearly the same architecture. So I will be focusing on the encoder part. So as a beginning, I will be start with inputs. So let's say we have an example, we have a sentence like Emre ate chicken. So if you have any familiarity with computer science, you know that we have to sometimes we have to change our data to numeric forms. For example, if you have a background on computer vision, we know that we are representing the colored image with multidimensional arrays, which each dimension represents a color space. So in here, we are representing our colored image with 3 channels, which are red, green, blue, RGB. So for our sentence, we have to do something similar. And we have to change it to a vector so we can manipulate. So one way to do it is just split the text into characters and then give them unique random integers. But there is also another basic way. Instead of just splitting the text into characters, we can also just split the our sentence into words and also give them unique integers. But actually, we need more advanced architecture to represent our words instead of just throwing some random integers to words. And this is word to break. For example, let's think about the word apple. How would you describe an apple? You can say that it's a fruit, or it's a corporation, or it's green, right? So we can actually, instead of just throwing some numbers to represent a word, we can assign it to different features to represent it. So if we assign probabilities to our words about some features, we could enrich our representation of a word. As I said, instead of just throwing some random integers, we can represent our word with some of features. So there is a famous illustration for the word-to-vec architecture. Let's say we have these two words, king, man, and woman. And their word vectors, like in the previous slide, we have some features and this vector representing our words. So if we subtract the man vector from the king and add woman vector, as a result, we are getting the queen vector. So from here, we understand that if we enrich our word representation with some features, we can get intermediate results. So we can generate text with more possibilities. So let's go back to our example. If we apply word-to-vec, we get these vectors. These are just random for visualization. And we call these vectors feature vectors as embeddings, our word. So we did the embedding part. So here's the positional encoding. And notice we didn't add any information about the position of the words. So for us, for human eye, we see that Emre 8 çıkın and 8 çıkın 8 Emre is different, have different meanings. So, but our model doesn't know that. So we have to add some information about the word position. Paper introduced us to use sinusoids for the define our position. So the sinusoids have two properties that we can use. One of them is our position vectors are will just between the -1 and 1 range. So we cannot face with exploiting gradients in our training group. And also we get with using sinusoids in our for our position vectors, we get unique position vectors for each of our word vectors. So if we observe our formula, we have three variables. One of them is pos, which is position of the word, and I for the index for our word embedding, and the model is the vector size of our word embedding. For example, for the Emre, we are getting 1010 as a position vector, and if we apply this positional encoding to all of our words, as a result, and also adding this position vector directly to our embedding, we got position and relationship aware embeddings. So after the positional encoding, there is a actually self-attention part. And in here, before going into the attention model, I could give you an example. So let's think about you are going to buy a keyboard from the Amazon website, and you are just writing down the keyboard to your search to the Amazon search bar, and this will be your query. And in the background, the Amazon website takes your query and compares with your its database and returns you all the possible results. So in their database, they have product names, product features, product description, product text, etc. And they are just taking your query and comparing with their features, and we call these features as keys in our case, and returns you all of the relevant products, and we call these products as our values. So in the attention module, we actually doing the similar thing. So we are trying to find which words correlates strongly with your with our other words. So with doing that, we actually forcing our model to pay attention to those relationships. And by doing that, our model for example, he can find correlation between Emre and he, something like that. So with the Amazon example, we had query key values. In the attention model, we just find similarity between query and key vectors and then just multiply with them. Actually, in the original paper, we have two extra properties. One of them is softmax and the other one is scalar factor, dk. So I will be talking about. Let's go back to our example. And in here we have these word embeddings, and if we merge them, we get our sentence embedding. And after that, to get our query key and value vectors, we just have to copy our sentence embedding and pass them through the linear layers. These linear weights have randomly initialized at the beginning of the training loop, and we just multiply them to get our linear transformation. After doing these calculations, we get our query key and value vectors. So as you remember, we have to find similarity between query and key vectors. We just get our query, which is Emre, and then just multiply it with each of the keys. So for example, this is Emre and 8. We are just transposing it our K to multiply and A and each. By doing that, we are finding our attention scores. So after defining the attention scores, we have to scale it down because the authors noticed that the dot products grow large in training loop. So we have to somehow scale it down to not to face with exploding predictions. So we are just dividing it by the dimensions. After that, we are finding the weighted version of our inputs. We are just applying softmax function to get the probabilities between 0 and 1. And for the last step, we are just multiplying our attention scores with value vectors to get the final version of our word embedding. By doing that, actually, we are just by multiplying this value vector with attention scores, we are just telling our model to pay attention these places. So after doing this step for all of our queries, which are the words of our sentences, from our sentences, we just concatenate. So this was the self-attention module, but there is also a thing called multi-attention. In here, we are just doing the same thing over and over again. Not in that order, but we have to do it individually. So by doing that, let's say we are doing this for 6 times. We are getting our example sentence, Emre ate a chicken, and copying it by 6 times and giving it to 6 different attention modules. So by doing that, we are aiming to get to know the different aspects of our sentences. For example, again, if you have a computer vision background, you know that the convolutional neural networks have some kernels, filters, and they are focusing on different aspects of an image, like edges, curvatures, eyes, ears, nose, etc. So in here, we are trying to do similar things. So for example, we are just want to know the relation between subjects and verbs, like placement of verbs and etc. So this was nearly all the encoder part. There is also feed-forward networks, but I'm not going to talk about them. Instead, I will be talking about some example about two text generation models. So first of all, we have these two models, which one of them is GPT-2 English, which mostly trained on Wikipedia data from the internet, and the GPT-2 Turkish one. The Turkish one is fine-tuned on Turkish plays, Turkish novels, Turkish stories, etc. and actually not only Turkish, but translated novels, plays also. So I'm trying to do here is giving one input word, which is Turkey in our case, and expecting from the models to continue the sentence. So in the left one, the English one, it says Turkey, a former member of the ruling party. Actually, I didn't put the rest of the table here. It was talking about something about current ruling party, which most of you know, and it was talking about something about fascism or something like that, but I don't remember exactly. But from here, we can actually see that these models are influence the data a lot because in the Wikipedia, the GPT-2 English model can learn some maybe the wrong information about the Turkish, so the model generates. So in the right one, we are as I said, we fine-tuned on some stories, plays, novels. So it says Türkiye bu bir tür hastalıktır, something like that. We see that it tries to generate a story from the input word Turkey. So in here, I'm giving two inputs. One of them, I love you but for English, and seni seviyorum fakat Turkish. And in the left one, we see that the English says, GPT-2 English says, I love you but I'm not going to let you go. And it's okay, it's cool. But in the right one, we see that it says seni seviyorum fakat bu da beni tiksindiriyor. Which we can see that it's influence from Dostoevsky or Tolstoy or something like maybe Ömer Seyfettin, I don't know. So that was my presentation. Thank you
Very much.